Good afternoon to everyone. I'm Concetta Messina from Università of Palermo, Department of Earth and Sea Science. Laboratory of Marine Biochemistry is located in Trapani, and I am also honored to be also part on behalf of the European Society for Marine Biotechnology. I would like, first of all, to thank the organizer of the course and in project EcoeFISHent as a very important project that meets goals related to the circular economy. So I feel very happy to be part of this training. So first of all, I would like to present our laboratory, why we are involved in this course, because our research line are in line with some of the topic of the project EcoeFISHent. And our laboratory is devoted to research applied to fishery and aquaculture, moving to all value chain from animal welfare to quality of the product. And from this, we more than 10 years ago, we started a research line related to the extraction of bioactive compound from marine organisms. We have also a platform for cell culture and alternative method to evaluate stress and welfare in marine organisms. But focus of our research is represented by fishery product, both from fishery, aquaculture, processing industry, and bioactivities included in marine bio-based product, as a fish and aquatic product are a key component of the global food system. And in the last decades, we have recognized an increased demand for fish food, for fish product, that has determined a significant increase of the fishery production, both from fishery and aquaculture. And starting from 16 up to now, the aquaculture production has more or less reached the production of the fishery, becoming one of the most important productive sector for the marine product, and determine also the development of a new sector of production that's related for algae or marine plants that also in Europe are becoming really interesting. So this interest for the global population on in regard to the marine bio-based product, fish product, and marine bio-based product is due to the well-recognized role of fish and related product to our health and welfare. But in any case, apart the benefit for health, fish and aquatic products are a key component of the global food system in order to ensure that all population can reach or cannot be behind the global food security goal. Just to remind the definition of food security from the FAO. So food security exists when all people at all times have a physical and economic access to sufficient, safe, and nutritious food that meets their dietary needs and food preferences for an active and healthy life. And for many populations, especially the population that at low income, fish represent the only source of proteins. So this food commodity is very important for the global population. The consumption expansion in the last decade for sure was determined by an increased awareness of the consumer in relation to the health benefit of fish. And so the production followed the request for fish product. And this was accompanied by an technological development in the fishery and aquaculture sector. This has determined also some economic effect, so the rising income worldwide, and at the same time attention for the topic related to the reduction in loss and waste, because consumer became more and more aware about the need to become more sustainable and also to avoid food waste. And especially if we take into account that the provisional for the state expected for the 2030 give aquaculture increase in terms of production as a sector that could meet the increased demand for fish food product. In this regard, the the global society, the scientific society, the researcher, but also the government are looking for solutions in order to let that not only today but also tomorrow and the day after tomorrow we can ensure fish and fishery product to all the population. Among the solutions we can consider, so of course, a proper management of activities related to the aquatic production, both for fishery and aquaculture, but also the increasing of consumer awareness for the topic related to the sustainability of the consumption, the utilization of fishery management along the value chain, and so on, and a better utilization and valorization of non-food resources. So, sorry, it's up. Okay. In relation to this awareness and in relation to the problem to be solved in the past decade, the Blue Growth Agenda has defined some priority areas intended to unlock the potential of the blue resources. And among these priority areas, we had also blue biotechnologies and aquaculture that represented two of the most important target sector. One, the society addressed forth in order to render the production and then consumption more sustainable. The principles of the Blue Growth are also contained in the 2030 Agenda for the Sustainable Developmental Goal, specifically for the goals 12, responsible consumption and production, and also for the goal 14, life below water. That is the most important goal in the agenda related to the marine resources. But for sure, a sustainable development requires a coherent and an effective cooperation among countries and institutions. So we need to work all together, but especially involving all stakeholders, so institution, research, the sector of education, and the civil society. And the principle of the 2030 Agenda specifically for the implementation of some good practices for the better management of the blue resources are contained in the roadmap for the blue transformation that are a series of measures and guidelines that would like to promote an innovative approach that can expand the contribution of aquatic food system, focusing on food security and nutrition, and in order to reach healthy and affordable diet. So, which are the goal, the objective of the blue transformation? The roadmap for blue transformation focus on sustainable aquaculture expansion and intensification, an effective management of all fishery practices, and an upgraded value chain. The focus of the blue transformation represented by seafood. And why seafood? Why eat seafood? Because seafood in general, so fishery, mollusk, algae, and all the edible organisms in general are for sure highly nutritious. They contain essential and very important in terms of effect on our health components. So starting from a component of the proteic fraction, so amino acid, and that are very digestible or high quality component related to the proteic or nitrogenic part. We have also and the role of the lipidic fraction of fish and marine products that are represented by the unique role of essential fatty acids, as marine organisms are the only organisms that contain the polyunsaturated omega-3 fatty acids that are indispensable not only for human but also for fish, so are indispensable for aquaculture. And at the same time, marine organisms, mainly, mostly fish, contain essential minerals that are indispensable for to meet our nutritional requirements. So the strategies of the FAO for the blue transformation for sure focus on SDG 14, but mostly on aquaculture. And the strategic framework for the upcoming 10 years focus on a better production, better nutrition, better environment, a better life in order to move along all the value chain that go from the production to health of the human, of the organisms in general. So which are the goal of the blue transformation? First of all, to produce within the aquatic food system sustainable production, so sustainable fisheries, sustainable aquaculture, but afford also a sustainable trade and value chain. Within this general topic, we have the attention of the international community for aspect related also to economy, social aspect, so to produce in environmental, economic, and social more sustainable manner, produce more safe and nutrition organisms, ensure also an safe and proper condition of work, decent work to the worker, and to produce sufficient aquatic food, and last but not for importance, one aspect that is the most important focus of our lecturer today, to reduce the food and the food waste and the food loss as a strategy to meet the zero waste goal. Which are the intervention in relation to the fishery, so focus on an innovative and sustainable fishery techniques, arranging or managing industrial fisheries, changing fishing practices, moving on a new model or updating the model for production in aquaculture, and moving also in the direction of more sustainable production of fish, and by giving attention also to other species apart the most consumed. And another important aspect of the roadmap for the blue transformation is the attention, more attention to the value chain, so the traceability, improve the action for the traceability, being able to track all the steps that the fish move on from the origin of the journey of the product from harvest to the table to the end consumer, harvesting, landing, the processing, the distribution, the retailing up to the consumer, with the goal to ensure quality and food safety, the consumer protection, a better responsibility for the players, for the actor of the industry, reaching the improvement of the management of the resources and giving support to the sustainability. For sure, the challenges that can be encountered are related to the complexity of the supply chain, the cost associated to the technologies, to take into account also the illegal, unreported, and unregulated fisheries, and move on reinforce education and awareness. So just in this area is belong also the training course that you are doing. So we are very lucky at the moment to contribute to the goal for the blue transformation. So just to give some example on how to move action from research to the industry to meet some of these challenges. For example, for the sector of the fishery, promoting the processing of low value species, so that belong to the low trophic level. So we have apart the target species, the well-known species that all of us consume. There are in each countries, in each coastal community, some peculiar and local fisheries that collect some species that have a low value in terms of income, but have a big value in terms of nutritional value. And at the same time, these fish species belong to the lower trophic level. So the promotion of the consumption of these species is a strategy to ameliorate the sustainability of the fisheries, and ameliorate the economic sustainability of the community that live about fishery, and at the same time are able to move the attention of the consumer from target species to more sustainable fishery species. So it is important to highlight that these strategies belong to very important European strategies and actions such as the FARNet that was applied along all the coastal Europe community in order to promote unknown fish species in the form of processed fish, fillet, transformed by producing functional food and so on, in order to produce new categories of fish product that can be more attractive for the consumer. In this way, by moving our attention from for example, salmon or tuna or cod, shrimp, and so on, we can promote the consumption of fish species that are more sustainable, and in the same time, we can multiply the number of fishery species present in the market, increasing also the economic sustainability. Other example related to the new action to do in the sector of aquaculture. So in order to meet the priority of food from aquaculture, we can move, we can have the example of the multi-trophic aquaculture system. So the integrated multi-trophic aquaculture is a model of aquaculture that combine the fat species such as fish or shrimps with organic extractive species, mostly mollusk, filter feeding organisms, and with inorganic extractive species such as algae or marine plants. In this way, by multi-trophic aquaculture system, we create a system of cultivation of marine organisms that is very similar to the natural condition, by creating a system that is more sustainable from environmental point of view, but also from economic point of view, because we reduce the impact, and the byproduct produced by fish can be eaten and filtered by mollusk, and the final catabolite of fish and mollusk can be used by algae for its own metabolism. So at the end of the productive cycle, in comparison with the classic aquaculture, we don't have only fish, but we have fish, shrimps, mollusk, and also algae. So more product with more sustainable way, reducing the environmental impact. And the byproduct or the secondary product obtained by mollusk, by seaweed, but also by other organisms that are put inside the multi-trophic system can be used not only as a food but also as an animal feed for the pharmaceutical, for cosmetics, and so on, especially algae or bioactive molecules that can be extracted from other organisms that can be positioned together to fish. And the blue transformation consider also alternative method to produce fish product and also the cell-based seafood, the cultivation of seafood in vitro, that is a new frontier to produce seafood in order to meet the so variable consumer needs and requests. Of course, we are in the phase of research, but this is another strategy that it is the case to mention as it becoming a reality. But moving on a challenge related to the zero waste as a strategy to ameliorate the sustainability of the aquatic resources, the nutritional policies for healthy diet recommend to reduce fish and seafood losses both during the production but also after the production and after the consumption. This because the residual both of the processing fish, of the filleting of fish, and also of the consumption still contain a huge amount of components such as protein, such as lipids, such as vitamin and mineral and antioxidant that are still useful for many industrial sector, for pharmaceuticals, for as an ingredient for food or feed, for nutraceuticals and so on. So the sector of the fishery, aquaculture, and fish processing generate a significant amount of byproduct that need to be well studied and well exploited in order to extract from this component the bioactive fraction that can be useful for many industrial purposes. And in this regard, aquaculture that produce fish in a very traceable system as a production from aquaculture very well controlled from the first step from the reproduction up to the arrival of the product in the GDO. Also, the fraction representing byproduct are well controlled and have a very high quality in terms of protein and lipid composition. So the research, but not only, also the government and institution are devoting significant attention to the valorization of this biomass that can be really interesting in terms of, first of all, of quantity, but also in terms of quality. In fact, if we take into account the principal resources of byproduct, we need to classify this byproduct in bycatch, that is composed by all the fish species that are collected by the fishery but are not adequate to be consumed because of the size, because of the species, or because are damaged. This bycatch is around 8% of the whole fishery. And after we have the processing of the fishery and of aquaculture. In fact, fishery processing for the production of packaged fish or shrimps and so on generate a variable percentage of byproduct that in relation to the species move from 25 to 55 percentage. And the same for aquaculture processing for the production of fish fillet generate a huge amount of byproduct that in relation to the species move from 45% to 60%. So the possibility to, first of all, collect all these byproducts, study, classify, evaluate the potential of this byproduct, isolate the most important component to be extracted with industrial process, represent a real possibility to do circular economy. In fact, as we reduce the production of byproduct by the reintroduction of byproduct in new productive cycle, we do per definition, circular economy. So we move from the linear economy model to circular economy model. And this is important from ecological and economic and social point of view. First of all, for the resources, because byproducts are still rich in proteins, in marine lipids that are very high quality in terms of composition. So, but which is the strategy of the research group that work in this field? First of all, we need to isolate, we need to focus on the value chain. So we focus on the biological biodiversity. As we isolate, we characterize, we focus on the value chain, we do the extraction of the bioactive molecules and the characterization. After the extraction, the characterization from chemical and biochemical point of view, we go on the purification and after or to the evaluation of the biological activities. So we move from the biodiversity to the biochemical diversity to be evaluated with a sort of test or in vitro or in vivo. In this way, by having the responses, we can link the biological biodiversity with the chemical biodiversity and with the pharmacodiversity in order to link the bioactivity, the biodiversity with the bioactivity. It is important to focus on all these steps because moving from the resources to the molecules needs a multidisciplinary approach. So if we consider that marine organisms are not only fish but also mollusks and also algae or plants, we need to have also competencies in classification of the organisms, and we need also to have competencies in chemistry and in physics and in biochemistry for the extraction, but we need to have also competencies in cellular biology, in biochemistry, molecular biology to do the bioassay and evaluation by biochemical, biomolecular indicator and instrument and protocols in order to evaluate the effect of these molecules in vitro or in vivo. So as we isolate, we focus on the natural resources, so we do the collection, the comparative extraction, and the quantification of. First phase, for example, in antioxidant, is the antioxidant extraction and evaluation of the antioxidant power by standard test, with a means of test intended to evaluate the antioxidant power of the extract. After we obtain the extract or the molecules, we test the power of these molecules in vitro or in vivo. And after to have the responses, we can proceed with the industrial transfer of the procedure. So the phase 1 is the extraction, the phase 2 is the evaluation of the bioavailability of the molecules in vitro or in vivo, and the phase 3 is the transfer of the procedure to the industry, so the application. So we can see some example of some case studies in my lab related to the application of the principle of the zero waste in the value chain of fishery and aquaculture. For example, we have set up protocol for extraction of fish oil and carotenoids from fish and shrimp byproduct that account for almost up to 40% of the production. And in some very strong value chain we have in Sicily, such as tuna, anchovies, and aquaculture and shrimps, we set up the protocol for extraction of fish oil and enrichment. We will see the protocol later in a specific PowerPoint. The extraction of astaxanthin from shrimps and setting up the procedure by short path distillation and supercritical fluid extraction, realizing some procedure and product innovative, and also to submitting a patent for some extraction. In this way, by recovery byproduct from the fish processing industry, we meet the goals 12 for responsible consumption and production. By pressured liquid extraction and supercritical fluid extraction, we have the transfer of the protocol to the industry. The result of this case study were published in a paper. We extracted and byproduct from farmed gill sea bream, and we set up the procedure for extraction of omega-3 of oil enriched in omega-3 by visceral oil. By short path distillation, we evaluate the properties of this oil in vitro for bioactivity, and the protocols set up was able to enrich the fraction of the omega-3 fatty acid significant way in respect to the raw oil. We will see this later. Another case study that referred to a procedure that was set up at industrial level was the extraction of astaxanthin from shrimp byproduct, and contemporary extraction of protein hydrolysate in combination with astaxanthin. We have set up some green extraction method by enzymatic hydrolysis for fish oil extraction and supercritical food extraction. So we were able to enrich the astaxanthin content in the extract, and we tested also the astaxanthin in vitro in cell culture for antioxidant and antitumoral activities. Another case study referred to the third strong value chain in Sicily, that is those related to the tuna production. So we worked on a farmed bluefin tuna byproduct. From this byproduct, we extracted the oil, and we did the pre-enrichment in omega-3. So sorry, I just jumping back a little bit, because also this the result of this study is in a paper, a published paper that I will share with the organization for giving to you. And the third case study is related to the extraction and enrichment in omega-3 of fish oil from tuna byproduct by oil extraction, urea pre-enrichment, short path distillation for that let us to obtain an enrichment in ethyl ester, and we did the evaluation of activity in vitro. And also this paper, also the result of this study are contained, are included in a paper that I will share with you. And overall, thanks to the research activity that belong to project related to national project on international project that belong to both Interreg and Horizon Europe, we were able to set up a procedure and protocols for extraction, separation, transesterification, molecular distillation, and enrichment by supercritical food extraction. So we have set up the procedure and protocol to extract, to produce at industrial level fish meal, fish protein hydrolysate, collagen, carotenoids, chitin, chitosan, and also antioxidant. In this way, we met and we meet, as we are continue to work, the European Green Deal goal that is intended to turn waste into profit and giving to the seafood processing sector not only sustainability but also development and economy, sustainability from economic point of view, by meeting the requirement for circular economy that is intended to refuse, reform, or reuse up to the recycling, putting again of the byproduct in a new productive cycles up to the final destination. In this way, if we reduce the amount of byproduct produced, we do circular economy and we increase the sustainability. Okay, this was related to the first presentation. Sorry, I needed to start with a new sharing a new file. And the new file, the new presentation is related to the byproduct in general, classification not classification, but is a presentation on related to general byproduct categories. Sorry, I need to. Do you see the shared file? I'm asking to the organizer, please.
No,
Okay.
no, I
Yes,
can't
yes,
see the file.
yes. This is sorry. This is a problem related to the when we share a new file, because each time we need to share again.
Okay, no problem.
Okay. So now it is okay.
Yes, yes, now we can
Okay.
see it.
Okay. Sorry for the trouble. Okay, if we go on the source of byproduct, we need to consider diverse categories and diverse sources. So first of all, more or less 60% of the global fishery go to the processing for food uses, and we need also to consider the introduction of the landing obligation from the European Common Fishery Policies. That is sorry, don't go on again. That limit the utilization of the byproduct. So the landing obligation of the European Common Fishery Policies was introduced in 2015 and was implemented in 2019. And that goal is to eliminate the discard from the fishery in order to suggest and encourage fishermen to fish more responsibly and avoiding the excessive or the bycatch to and move on to a more selective fishery to avoid unwanted catches according to the measure discardless. So it is estimated that at global level there is an average, there is a quota from 7 to 10 million ton commercial fishery catches that are discarded annually. And these discards are still rich in protein, lipid, and other bioactive compound that can be useful for many industrial purposes, reducing the discard, reducing the waste, and increasing the sustainability by reintroducing this biomass in new productive cycles. So fishermen discard fish for many reasons, or because the fish are smaller respect to the legal size, or because the fishermen don't have the quota assigned for it, or because fish are the so-called poor fish have a low market value, or because the fish are damaged, or because it's a prohibited species, and so on. So the landing obligation lays down a few rules that need to be highlighted and when studied in order to set new or an harmonization procedure among the diverse countries. But for sure, the fish waste generates some issues related to the environmental impact and also management issues that move from ecological to infrastructural and logistic point of view. For sure, the fish discard can represent a secondary raw material. So as a huge amount of fishery bycatch or processing byproduct are continuously produced and need to be managed in order to avoid environmental problem, and also to ensure and to increase the ecological sustainability and the use of the resources. So fishery byproduct can represent an interesting source of high added value molecules, a compound such as proteins, carbohydrates, collagens, polyunsaturated fatty acids, and so on, and represent a very important, efficient resources approach to manage the problem. If we take into account the component represented by catch, fishery by catch, but also processing by product, we have diverse tissues or organs. So it is important to differentiate first of all among species and system of production, because it is different to evaluate these in fish from the wild or from aquaculture in relation to the species from a scientific point of view, because diverse morphological characteristics means diverse impact of each component in the total weight. So we have the head, skin, scales, bone, viscera, that in relation to the size of fish, in relation to the species, in relation to the system of production, but also in relation to the season, can change in percentage. So fish bone can provide a valuable source of organic components such as collagen, gelatin, and as for the inorganic substances, they are mostly represented by calcium, phosphorus, or hydroxyapatite. Fish skin is considered a source, a very good resources of collagen and antimicrobial compound that can contribute to provide one of the most important barrier to the pathogens because it's the first barrier against microbiological attack. And fish viscera are recognized to be an important source of enzymes. If we move on the components of the biochemical components that are contained in a byproduct, we need to classify this component from biochemical point of view. So we have for sure the proteic or nitrogenic fraction that is composed by proteins or nitrogenic fraction. As far as regards proteins, so fish frames contain a significant amount of muscle proteins, the so-called side streams. And the fish proteins are generally used as a fish meal ingredient for aquaculture, a formulated food, or to produce fish sauce and silage. But another important component that can be obtained from fish byproduct from the proteic fraction is represented by fish protein hydrolysate. Fish protein hydrolysate, in fact, is a concentrated and purified form of proteins that can be obtained by subjecting by a treatment of proteins with enzymatic treatment that are able to do a cleavage of some molecular bond through biological processes. And the fish protein hydrolysate that are composed by small peptide with respect to the proteins, the word proteins, are granted about important pharmacological nutraceutical properties such as antioxidant properties, antihypertensive properties, but also neuroactive antimicrobial properties. So for sure, fish proteins are a good source for fish protein hydrolysate. It is a source of bioactive peptide. Some peptides obtained by hydrolysation are granted by antimicrobial properties. So the first family of peptides with antimicrobial properties discovered was some peptide against gram-positive, gram-negative bacteria. And we have also the possibility to obtain from a proteic fraction enzyme, especially from fish viscera, that are among the most important fishery byproduct. And the viscera contain digestive enzymes that can exhibit significant catalytic power at relatively low concentration. And the proteases are the most used enzyme in food, in detergent, and also in pharmaceutical industries. And from the whole body, we have the possibility to obtain lipids, collagen, hyaluronic acid, from the gut enzyme probiotics, from the fin collagen, calcium carbonate, and also for the skin collagen, gelatin, hyaluronic acid, and so on. Collagen and gelatin represent collagen, the most important structural protein, fish skin and bones, represent more or less 30% of the total protein content and is a biomaterial for biomedical application. So fish gelatin is also known to possess antioxidant properties, and collagen and gelatin are the same macromolecule in two different forms. So from, as an example, from tilapia, we can obtain from the skin that can be treated from the pre-treated skin. We can obtain the collagen. Other components are chitin and chitosan, especially from the fish scales, but also from shrimps, can be utilized for the production of bioactive products, including antioxidant and also anti-diabetic compound. So the adhesive nature of the chitin and chitosan, along with their antioxidant and antimicrobial properties, are very important properties for biomedical and pharmacological application. Lipids for fishery byproduct contain lipids in the form of fish oil, concentration and varies in relation to the fish species. And the lipids for sure is the most important, as contain the two most important polyunsaturated fatty acids that are eicosapentaenoic acid and docosahexaenoic acid, that are classified, that belong to the omega-3 fatty acid. And we have also possibility to extract and to obtain minerals, as the fish bone contain from 70 to 60% of mineral, including calcium, phosphorus, and hydroxyapatite, and so on. Another important component is represented by probiotics. So if we keep in mind the definition of probiotic are living organisms, microorganisms that when consumed in an adequate amount confer health benefit on the host. So if we take into account that especially the aquatic environment in form of probiotic contain phytoplankton, we have the definition of first probiotic acting in beneficial way. So the skin, gills, and all the gastrointestinal tract are main in which bacteria can play a probiotic role for the host health. So many works describe the function of the microbiota at the gastrointestinal level in fish and the potential application of probiotic in finfish aquaculture. And these probiotic exert a beneficial effect in relation to many pathologies. So for sure, some organs in relation to the microbiota they contains act as a probiotic itself. So a complex of variable bacterial community that inhabit the gastrointestinal tract of fish play a significant role for the host health and quality, because the health of fish is also related to quality, and take part in the diverse digestive processes thanks to the synthesis of bioactive compound that can have antimicrobial activities in different species, and also immunomodulatory effect and activity on growth performances. So production of microbial digestive enzyme that represent an important source of energy for herbivores, having also antibacterial and antitumoral activity, and also cardioprotective agent, and experimented for neuroprotection activities. Also yeast contained in fish skin and gills have an important role, as the mucous layer of the skin provides a broad spectrum of antibacterial activities, and the presence of bacteria with antibacterial properties on the mucosal surface of the gill was also being reported. So it is another important case study. So we can move to methodologies for extraction. As a methodology for extraction, recently the method used for extraction and characterization for industrial fish transformation have been examined, and they focus mostly on more sustainable technologies. So the use of fish resources for responsibly and efficiently is necessary in order to establish a functional and safe method for the proper extraction of nutrient and other bioactive compounds. So it is more and more indispensable to move from the standard method to green method. So green method have been introduced also in respect of the Green Deal on the circular economy. So if we move from method for extraction, we can differentiate from a standard method to unconventional method. So as for traditional method, we have the method with solvent or with enzymatic hydrolysis. The solvent extraction is the most common techniques used both for extraction of proteins and lipid fraction from fish waste. And extraction by enzymatic hydrolysis is largely used techniques for the extraction of fish oil and also for proteins. As a green method, we have some technologies. So green extraction technology are safe and usually combine the high quality of the extract of the product with the safety. So are based on discovery and design of extraction processes and reduce the energy consumption, allow the speed and efficient processes, and combine the utilization of alternative solvents, ameliorate the environmental impact, use renewable natural product, and are usually more selective and in terms of isolation of the compound. Usually the green methods are based on a series of principles that let to define them sustainable. Use renewable resources, use biodegradable solvent, reuse of the energy released in the extraction processes, production of co-product or byproduct, not waste, reduce the number of operations, and the extracted product must be unaltered, biodegradable, and not contaminated. Among these methods, we have the supercritical fluid extraction, the microwave assisted extraction, and also the ultrasound assisted extraction. So the supercritical fluid extraction is mainly used in the pharmaceutical and nutraceutical sector, and it is widely used especially in the fish sector for the extraction of fish oil and antioxidant molecules. And while the microwave assisted extraction is a more limited use in the recovery of bioactive molecules from fish waste, because from this process, from the extraction to the field of application, the procedures are still under scalability, but it's still considered a better method than traditional techniques. And ultrasound assisted extraction is an emerging technique that allows the extraction of many substances such as antioxidants, vitamins, mineral elements, pigment, and so on. So the green method for sure are the most highlighted ones, are seen with a great potential in the circular economy toward the zero waste approach. If we consider that more or less 50% of the global production is represented by farmed fish, and that more or less the 50% of the biomass is not consumed and is destined to become a waste, it is indispensable to plan, action, measure, and activities aimed to collect and valorize all the byproduct that comes from all the value chain, and for the production of ingredients for food, for feed, but also for pharmaceuticals and biomaterial. And so in food and nutraceutical industry, we have the example of fish meal and fish oil that represent one of the most valuable products obtained from marine byproducts that are not used for human consumption. It is estimated that each year more or less 60% of fish meal and 80% of fish oil in the total production are consumed as aquaculture feeds, and this percentage is expected to increase in order to guarantee the future of aquaculture growth. And as far as regard application in pharmaceutical and biomedical industry, it has been reported that fish consumption is important in order to guarantee health and welfare, and that the consumption of fish generates waste as a byproduct that need to be must be valorized, especially for the extraction of the omega-3 and the two most important essential fatty acids, APA and DHA, eicosapentaenoic acid, docosahexaenoic acid, that are proved to be very beneficial for immune health, for heart health, for the total, the global welfare, for the joint, for brain, for the eye, and the consumption of fish and fish-related compounds are active against obesity, to prevent cardiovascular diseases, as a neuroprotective effect, and cancer prevention. So DHA is important for the optimal neurological development in children, and it is recommended for pregnant women, and enrichment in infant formulas to contribute to the normal development of the eye. So docosahexaenoic acid and docosapentaenoic acid are the key component essential both for human and for fish. The APA, eicosapentaenoic acid, improve the cardiovascular function, the response to chemotherapy in patients that are affected by cancer, and reduce the risk to develop certain type of cancer. So, fish processing can find application also in other industrial uses, as the high demand for fish originates an overexploitation of marine resources. In some cases, the fish processing industry use only some part of the fish while the rest is discarded. So fish byproduct can be used also as a source of biodiesel. Biodiesel consists of monoalkyl ester of fish oil that can be synthesized from the edible and inedible waste oil, and these represent non-toxic, biodegradable, and renewable energy resources. So in the fishery sector, circular economy is a series of actions that, starting from the resources, can generate product and from this application, and is a strong driver to reverse the not sustainable trend of fishery sector toward a growing negative impact on the aquatic environment. So by reintroducing byproduct new value chain, we can contribute to increase the sustainability. And circular economy approach is based on eco-design, on modularity, versatility, the use of renewable energy by an ecosystem approach, and recovery of the material. This is an example of biorefinery, the fishery bycatches and processing byproduct, and can be considered a real ingredient for new biorefinery. So we can combine, for example, extraction of omega-3 with extraction with the bioactive molecules from other value chain from the agro-food sector. So we can obtain a fish oil that is enriched in antioxidant and address the remaining fraction to the production of biodiesel, biogas. And in general, the high content of water in the fishery discard and the presence of mineral, of course, require a proper technologies for an efficient energy conversion, but of course, to address the byproduct to the diverse value chain needs preliminary treatment that can be evaluated case by case in relation to the industrial sector we want to address each fraction of byproduct. Okay, so I would like to propose a break, if the organization agree.
Yes, of course, we can take a
Okay,
break.
so we can take a break. So if you agree, we can meet again around 16, 40, 45. It is okay?
Yes, it's okay, perfect.
Okay, see you in 15 minutes. Thanks so much. topic related to the general aspect related to the byproduct that can be obtained from processing fish, going on some other details and aspect. An example, we can move on some other aspect related to the fish collagen application. The collagen is one of the most promising natural biomaterial to use it in the sector of the natural scaffold that include gelatin and are of course biosafe, biocompatible, and is granted about a very good antigenicity. Some benefit of the collagen, and these are some species where we can obtain it at pilot and industrial scale, is the promotion of the cartilage production and regeneration, the production of biomedical hydrogels, promoting the bone healing, the skin generation, and have also some antibacterial activities. Other applications of collagen in industries are related to the pharmaceutical, cosmetics, nutraceuticals, but also as a food additive and as a collagen and chitosan coat. Moving on peptides, again, some peculiar aspect related to peptide. So peptide were isolated from, especially from species such as pollock, sole, salmon, halibut, and tuna, both from the whole body waste or from some specific parts such as bone or scale or head or gonads or viscera from these species. And fish protein hydrolysate are very interesting in terms of market size. If we take into account that in some years ago the trading related to this pharmaceutical compound ranged around 420 million, and supposed to increase in the upcoming year. And the extraction method for the collagen involve an acid-alkaline hydrolysis by using acidic or alkaline reagent, and enzymatic hydrolysis by using enzyme to hydrolyze the wastes, and a fermentation by microorganisms as a source of enzymes. So after the extraction, it is indispensable to proceed with some purification step that can be or the ultrafiltration or the nanofiltration or gel filtration that are used to purify peptides according to their molecular weight. And another alternative is the ion exchange chromatography. It is used to purify peptide based on their net charge. And after HPLC, high pressure liquid chromatography to separate compound based on their hydrophobicity and hydrophilicity. Here we have some application of fish peptide. So on the left column we have the compound with the acronym that identify the commercial product, and in the second column the byproduct of origin, the biomass of origin, the species of origin, the application. So the first compound isolated from the skin of the skipjack tuna has antimicrobial properties. The second one from the skin of the yellowfin tuna is granted also by antimicrobial properties. And the third from a not specified byproduct of the Scombus combus has antibacterial properties. The fourth product, peptide from the skin of salmon, is granted about anti-hypertensive properties. And the next one from the frame of the cod, an hydrolysate with the average weight of the hydrolysate of 30 kilodaltons has antioxidant properties. And an hydrolysate with a molecular weight ranging in between 1,000 and 10,000 kilodaltons, from the bone of the yellowtail as anti-hypertensive and antioxidant. So the peptide obtained from the skin of salmon evidenced also some neuroprotective properties, and we have also other applications such as anti-cancer, anti-hyperglycemic activity, chondroprotective, calcium binding, anti-diabetic, anticoagulant, and so on. The chitin is an odorless and tasteless aminopolysaccharide, white color in its pure state, composed by N-acetyl glucosamine unit and monomer linked by beta bonds, and is considered the second most abundant high molecular weight natural a biopolymer after cellulose. So an important chitin derivative is the chitosan that can be obtained in the lab by the acetylation of the chitin. And both chitin and chitosan are basic in terms of charge. So it is estimated that the chitosan global market is another sector very important related to the possibility to reintroduce marine byproduct in the sector of pharmaceuticals or nutraceuticals and so on. As it is estimated that chitosan global market is increasing in the upcoming years, and annual production account for 2,000 tons, with the main sources being shrimps and crab shell residuals. And the main sources of chitin and derivatives are crustaceans and insects that provide an exoskeleton constituted of chitins. And recently, the fish wastes have acquired also great attention as a potential sources of chitin and derivative, with a particular regard to the fish scales. As far as regards the extraction method, the extraction of chitin requires the removal of some associated component, the two sequential chemical steps, so the proteinization for the removal of the proteins, and then the mineralization for the removal of the inorganic component. In some cases, it is indispensable to add another step for the colorization, the dorization, that is applied to remove the pigment, and the experimental extraction procedure is pivotal for the final application, because the purity and crystallinity level depends on it. So which are the fish chitin and chitosan applications? So first of all, medical, pharmaceuticals, but also in the food and cosmetic industries, in nutraceuticals, also for bioremediation, for tissue engineering, and these applications are dependent on the biological activities of this compound, that are antimicrobial, antioxidant, antibacterial, antifungal, antitumoral, antithrombogenic, anticholesterolemic, have bioadhesivity, immunoadjuvant, and so on. And it is important, don't forget that chitosan is used also as a food supplement, or for drug preparation, or for water treatment, and also for environmental recovery. So the beneficial properties of the chitosan are related to its properties to act as for food preservation, for the packaging, and as a color stabilization agent. Chitosan is biocompatible and biodegradable, is a film forming capacity, and is also a barrier against gas and aroma transferring. Chitosan has an higher solubility in various acidic solvents, respect to the chitin that is very less soluble, and possess some antimicrobial activities against many pathogenic microorganisms. And the film obtained from chitosan show flexibility, resistance, and an excellent ability to form oxygen barrier. Moving on fish oil, one of the key components of our activities, the fish oil is produced principally, mostly to have availability of the most important bioactive class of compound, the polyunsaturated omega-3 fatty acids that are the strongest compound for health both of human and fish to cover the nutritional requirements. So fish oil can be extracted from all the components of byproduct in a diverse quantity in relation to the species, in relation to the size of fish, in relation to the fat level of the fish, because we have a lean fish and fat fish, and of course fat fish store a huge amount of fat. While lean fish accumulate fat mostly in the liver, and so the liver of lean fish is the principal source of fish oil, such as cod. And so it is indispensable to verify the amount of lipid content in each fraction of byproduct. So the global fish oil market is huge, because the fish oil is used both in aquaculture, but also for the production of soft gel rich in omega-3 for human health, also for farming of other animals. In any case, the European community produces 120,000 tons of fish oil each year. So this production is driven by the great demand of fish oil, mostly as an ingredient for aquaculture industry. So it is important to have adequate availability of resources for fish oil production, and fish oil providing to the most important sector requiring this component. So the oil and fat available in fish and in fish byproduct depend on some aspect, on the fat of the specific fish species, on the distribution of the fat in fish part, on age, sex, nutritional status, health, and also the season of the year and the method of production. So wild on farm, because usually farmed fish of the same species have an higher level of lipid in respect to the wild of the same species. So fish oil contain triglycerides and fatty acid at a variable amount, phospholipids and glycerol ether and wax ester, and the lipid composition is different among species due to the large quantity of omega 3 and omega 3 fatty acids. Sorry. So docosahexaenoic acid and docosapentaenoic acid are considered essential both for fish and human, because human and fish cannot synthesize. And these fatty acids cover essential role that cannot be substituted, exerted by other components. So it is indispensable that both fish and human have an adequate intake of this compound by diet or by supplement. So the best source of omega-3 of this essential component are salmon, herring, mackerel, anchovies, sardines, and tuna. So in general, pelagic species, and that are more fat respect to other, and that have an higher concentration of this fatty acid. So the applied technologies that we can use to extract omega-3 fatty acid are enzymatic hydrolysis, supercritical food extraction, and microwaves, as we have seen in the previous presentation. And each technologies has pros and cons. So the advantage for enzymatic hydrolysis is quick and easily reproducible, avoid the generation of chemical waste, and contribute to the fish waste valorization. The disadvantage is that the extraction of omega-3 fatty acid by enzymatic hydrolysis is very expensive. And the other techniques, supercritical food extraction, has the advantage that is to reduce the lipid oxidation, provide a selective extraction, and avoid the co-extraction of polar impurity, but the yield are not too much, are not high in respect to other techniques. So the microwave extraction has the advantage to be a clean and green method and give high yield. Looking at some fish oil application, as a fish contain a variable amount of fat and 50% of body weight is represent waste, we can have the possibility to address specific byproduct to the production of oil with certain specific activities. For example, it was demonstrated that diet high in fish and marine omega-3 is linked to a lowered risk of cognitive decline and Alzheimer's disease. As far as regard the fish oil generated by viscera byproduct, this supplemented in animal feeding contribute to reduce the cholesterol content and the triglyceride in the final product. So the cod liver oil obtained from the liver of fish is if supplemented in bacterial grow media for the production in biotechnologies, is able to produce lipase. And lipase is an enzyme that is useful for many purposes, for production also in the food sector. The tilapia oil, extracted by viscera, fin, heads, skin, scales, and mixed waste, was used as a biodiesel. And we have also, some sulfate that obtained from fish waste can be used also as a lubricant. And enzyme, as specified before, are a very high quality compound, and it is only thanks to a good bio and extensive bioprospecting of the aquatic animals and organisms that we can approach a proper discovery of the enzymes contained in all byproduct that can be used for many biotechnological applications. So the internal organ, specifically stomach, intestine, and other visceral component are the most important fish byproduct in terms of number of and categories of enzymes that can be found in this byproduct. We need to take into account that the enzyme market is increasing for the upcoming year in significantly respect to the previous year. Other enzymes interesting for many applications for biotechnology, but also for food, feed, pharmaceuticals, and so on, are lipases that catalyze the hydrolysis of ester bond in substrates. Lipases show specificity in terms of fatty acid, in terms of nature of the alcohol in the molecule, and have also stereospecificity. The proteases catalyze that are other enzymes that can be isolated from the viscera and the byproduct of fish. Byproduct catalyze the hydrolysis of peptide bonds, and are referred as exopeptidase or endopeptidase in relation to the target of its activities. As digestive proteolytic enzymes from fish byproduct belong to some diverse group. We have the aspartic proteases such as pepsin or catepsin, the serine proteases such as trypsin and chymotrypsin, digestive proteases, thiol or cysteine proteases such as calpain and catepsin, and metalloproteases such as decollagenases. In fish, we have availability on some proteases. So the pepsin is located mostly within the stomach and has a greater activities in acidic condition. And we can differentiate the pepsin 1 and pepsin 2. The trypsin is involved in the hydrolysis of peptide bonds in the carboxyl terminal ends, has an essential role in the digestion of ingested proteins, is responsible for the activation of precursor form of several other digestive. The collagenases are capable of hydrolyzing the polypeptide backbone of collagen without denaturing the protein, and are classified in relation to the activities and to the target. We have the metallocollagenases and then serine collagenases, and after we have the chymotrypsin. So the fish enzyme application are various. So we have the use of the enzyme include some development of some industrial processes as alternative to mechanical chemical treatment, which often cause damage to the product. So, for example, the pepsin extracted from the stomach as a source of byproduct can be used for the descaling or for the production of the caviar in fish industry. The pepsin extracted from byproduct of from the viscera is found application in the silage production. From the liver can be obtained the uracil DNA glycosylate that found application in molecular biology, and the trypsin from the pyloric cheek of fish for fish hydrolysate production. And from the intestine, pyloric ceca, and liver, we can obtain diverse lipases that contribute to the potential lipid biosynthesis and the fatting of fish skin. So for the production of fraction purified in terms of lipid. So as a fish, as a waste framework directive, it is recommended to prevent the generation of waste and reducing the generation of waste, so the possibility to work with byproduct in order to isolate, purify, scale up the process at pilot scale, from pilot scale to industrial scale, let us to feed the new productive cycles that or other biorefinery that can generate circular economy and can reduce the environmental impact and can contribute to ameliorate the sustainability from the social to economic to ecologic point of view. So I need to move to another presentation. So I'm wondering if there are questions about in the meanwhile I'm moving to another presentation. I don't know.
For now, there are no questions from the participants.
There are no questions. Okay, I move to another presentation that is related to, okay, I can show okay, specific case study obtained in our lab related to the protocol used for the extraction of fish oil from byproduct. Do you see presentation? Excuse me? Do you see the presentation?
Yes, we can see the presentation.
Okay. So now we move to a specific case study on extraction of fish oil from fish byproduct. First of all, why we are interested in fish byproduct for omega-3? Because omega-3 belong to the sea. environment. So omega-3 are linked from ecological point of view to the sea environment, while in the land we found fatty acid that belong to the omega-6 series. So for this reason, but fish need omega-3, and we can find omega-3 from ingredients that have marine origin. So are indispensable for fish to complete the nutritional requirement, increase immune defenses, and improve also the organoleptic quality of fish. So the global demand for fish oil has posed global concern for the finding new resources for omega-3, both for ecological and ethical point of view. We have yet extensively talked about processing byproduct, but in farmed species we have a good source of omega-3 because farmed fish have a constant percentage of omega-3. So also byproduct have these characteristics. Thanks to a national project on innovation in aquaculture, we had the possibility to map in the flow of omega-3 from the diet to fish by realizing a mathematical model of dilution of fatty acid for omega-3. So we characterized the flow of omega-3 from the diet to fish, and we analyzed the fish and the byproduct of all fish for 3 years before to arrive to the identification of fraction of byproduct from which we can extract the fish oil thanks to short path distillation techniques. We focused on viscera and we implemented the techniques for extraction and enrichment in omega-3. So we moved from the fish byproduct from viscera. We applied the short path distillation. So we refined the raw oil in a refined oil that, thanks to the qualitative parameter related to oxidation, meet the nutritional requirement for the EFSA. So we were able to obtain a food grade oil. And an oil that was enriched in omega-3 fatty acid in respect to the raw oil. And the results of all these protocols contained are included in a paper that I will share with you with all details related to the process. What that is important to highlight is that starting from raw oil to the enriched oil with the short path distillation, if you look at the first circle, we have one of the most important saturated fatty acid, that is the palmitic. This was significantly reduced after the process of enrichment, and at the same time the fraction of eicosapentaenoic acid had a significant increase after the short path distillation, and the same for DHA, that increased significantly from the raw oil to the enriched oil after the process of short path distillation. We have tested the enriched oil in vitro and in vivo, and we scale up on industrial scale the process. And as a result of in circular economy processes, we fed this byproduct also to we included this byproduct and also oil to the industry related to the formulation of fish feed, aqua feed for aquaculture. And so we were able to, this is the result obtained with the tuna byproduct in terms of metabolisms, lipid metabolism. So we demonstrated that omega-3 enriched oil reduces adipogenesis in vitro. So this meet the well-known effect of omega-3 that are anti-adipogenic, so a good result in terms of nutraceutical effect. But we fed also insect insect larvae and the black soldai flyer Hermetia illucens with the byproduct from this byproduct of these value chains, as is well known that insects are new resources for the aquafeed sector. So we were able, by substitution of the diet with byproduct, to obtain a diet increased the level of omega-3 fatty acid in respect to the raw to the insect fed with cereals. And the most important aspect was that also the Hermetia illucens, so the insect prepupae, at the end of the trials resulted with a modulation of the biochemical composition. So we were able to increase the level of omega-3 fatty acid and the two indispensable omega-3 fatty acid, EPA and DHA, in the body of Hermetia illucens prepupae, attesting its suitability as an ingredient for fish meal and fish oil for aquaculture. So meeting another result related to the circular economy possibility for omega-3. So we, in this way, we have tested the possibility to include omega-3 fatty acid for pharmaceuticals, for nutraceuticals, and also for the aquafeed production, that are the three most important pillar for a circular economy, and also for cosmeceutics, of course. So as we have less than 10 minutes left, I think that we can conclude by inviting